Okay, we're going to talk about resistance this time. What is resistance? Resistance is literally the resistance to the flow of electrons. All right, again, when we talk about stuff flowing in a circuit, we're going to pretend that a particle of charge called a coulomb moves. That's not really what it is. A coulomb is a lot and a lot and a lot and a lot of electrons, but it's easier just to pretend there is a particle called a coulomb that moves. All right, but we have a circuit that's made up of a battery, and that battery is connected to, say, a light bulb. And this light bulb will shine. And this light bulb is an example of something that has resistance. If this light bulb weren't here and you hook this up, I'm sure you've all done this. You take a battery, you put a paper clip on both sides. The battery gets really, really hot because that paper clip has a very low resistance and a bunch of current just goes through it. The electrons just go through really fast and it heats up. Well, your light bulb also heats up, by the way, right? And when it heats up, it gives off light, but it has a higher resistance than the wire. It impedes the flow of the electrons, so the electrons end up going slower through that light bulb. What determines something's resistance? The resistance is determined by one, the material. The material is very, very important. If I stuck this marker in my light socket, you wouldn't expect me to get electrocuted, but if I went over there, grabbed a fork, and shoved it in the light socket, you would expect me to get electrocuted. You know that some materials conduct electricity, and some materials don't. Some materials conduct it really well, and some materials don't. So the material determines the resistance. The temperature. It turns out that when it's hot and when it's cold, you're going to get differences. Oh, why won't this move? You're going to get differences in the resistance of the material. We'll talk about how that makes a difference. And I'm going to just say geometry. Is it, when I say geometry, I mean things like length and area. Okay, so let's talk about this. Material. Well, we know that some things conduct electricity, some things don't. Some things conduct really easily, some things conduct, but like not great. All right, so that's the material difference. The material and the temperature both affect something called not resistance, but resistivity. Resistivity is sort of like thinking about density. All right, if I have a copper block, this is copper, and then I have a bigger copper block. It's very clear that this copper block has less mass than this copper block. It's very clear that this copper block has less volume than this copper block. But what's the same about both of these copper blocks is the density. The density of them is the same. So resistivity is like that. The resistivity of this and this is going to be exactly the same. Will they have the same resistance? No. Just like they don't have the same mass. But their density is the same, even though they don't have the same mass. Their resistivity is the same, even though they don't have the same mass. So the resistivity is a material property, like density is a material property. It doesn't change with size, resistivity. Resistance does, but resistivity doesn't. Resistivity does, however, change with temperature. When we think about flowing charges, think about going to classes in the hallway. The hallway represents the material you're going to travel through. The type of material that the hallway is made of might make a difference. If the hallway were ice versus the hallway were, you know, just like a normal hallway. Hallway is ice, it's going to be hard to walk through because it's going to be slippery, you're going to fall a lot, it's going to take longer to get through. Versus the way the hallway is right now, it's pretty easy for you to get through. So that's like how resistivity is affected by material. How is it affected by temperature? Well, what is temperature? Temperature is the average kinetic energy of, get out of here, of the stuff. It's like how much they're moving around. When we have a really high temperature, stuff moves around a lot. And we have a low temperature, stuff is kind of still and it moves much more slowly. So the temperature is like the other kids in the hallway. You're going to walk from one class to another, and if the temperature is really high, those kids in the hallway are moving around like crazy, and they're just going all over the place. If they're just randomly going around all over the place, it's going to be hard for you to get to your next class. But if everyone stands perfectly still in the hallway because they're cold, it's going to be easy for you to get around all of them. So as temperature goes up, the resistivity goes up. Higher temperatures, stuff moves around more, and it's harder to get through because it's this jumbled mess. When the temperature goes down and they're all standing still, it's easy for you to navigate. It'd be like, if every car on the highway, I guess it's not it'd be like every car on the highway randomly weaving in and out at high temperature versus staying exactly where they should be at a low temperature as you try to pass them, okay? Length. You need to get to class, and your class is on the other side of the school. Are you going to get there in time? Probably not. So when things are really long, it's harder to get through them. The resistance is going to go up. Area. Area is like the width of the hallway. If the hallway could only fit one person at a time, it was really narrow, it'd be hard to get through. You'd have to be behind everybody else. You wouldn't be able to pass and you wouldn't be able to do anything. But if the hallway is really, really, really wide, you might not even bump into another person. You might not see another person because it's so wide. So as the area goes up, the resistance is actually going to go down because it's easier to go through. There's more ways for you to get there. It'd be like having more lanes on a highway. It'd be like taking a hose, and when you put your thumb over the end of a hose and it shoots out, it's because you built up a lot of pressure. You made it hard for the water to get out. So when you have a small area hose, it's a lot of pressure. It's hard for the water. When you have a big area hose, it's easy for the water to flow. More water can flow with a big area hose. So these three things, well, I shouldn't say material, but as temperature and length go up, the resistance is going to go up. As area goes up, the resistance is going to go down. It's easier to go through. The material and the temperature are what decide what the resistivity will be. The length and the area decide the resistance. And so we in physics class have a reference table with resistivities on it. Resistivity is given by the the symbol rho. That's a bad rho. It looks like a fancy P on your reference table, like a lowercase little fancy p. And the resistance of something, which is R, in ohms, right? The units of resistance is ohms, is given by the resistivity times the length over the area, right? As resistivity goes up, resistance goes up. As length goes up, resistance goes up. As area goes up, resistance goes down. And so if you have two things that are exactly the same material, one looks like that, and one looks like that, and let's just say they're the same area, same area, same area. Those aren't great, but I should make this one a little smaller. If they're the same area, this one will have a smaller resistance because it's shorter. These are supposed to be the same cross-sectional area. But if I have two things that are the same length, but one of them has a really big area, this one will have a bigger resistance because it's smaller area and they're the same length. And then if you had something like this, you'd have to do the calculation. Maybe I got bigger, but I also got longer. So who knows which one's going to be a bigger resistance? You'd have to compare. All right? Obviously, the units for length are meters, and the units for area are meters squared. That means if we rearrange this equation to solve for the units for rho, we would find the units for rho are meter squared per meter times ohm. We don't leave it like this. We cancel out one of these, and we say that the units are in ohm meter. So an ohm meter times a meter, you'll get meter squared, and the meter squared will cancel. It will leave you with an ohm, the unit of resistance. So this is what determines resistance, the resistivity, the length, the area, and again, the temperature. So on your reference table, everything's at 20 degrees Celsius. If the temperature were higher, we would expect the resistance to be higher. We are all done.